Okay, so we're talking about electricity and magnetism, getting an introduction to electricity and magnetism. The concepts, again, are abstract. That is, that they're not tangible. You can't hold an electron, except you can. You are electrons and protons and neutrons. We'll get to that. So people didn't know about this stuff. There was a guy named Democritus who thought that we were made of indivisible parts, and the Greek word for indivisible is atom. But he didn't have the experiments we have today. He didn't really know what that was. So it's interesting that we have these kernels of these ideas over 2,000 years ago, but it took a long time to develop and explore them more deeply. So, for example, the Greeks get a lot of credit, but they weren't the only ones in the game, right? But they did some great things. Supposedly, there's a guy named Magnus, who I think was a shepherd, I don't know, and he lived in a part of Greece called Magnesia, and that was maybe 4,000 years ago, and he found these chunks, these rocks, these bits that would, attract and repel, and he found these crazy things. They weren't as good as these, since it's neodymiums. But and he'd go, wow, that's pretty well. I mean, I imagine some people freaked out, like, is this magic or something like that? Because people tend to freak out about stuff. So this phenomena was known, but they didn't know anything about it except, these weird things. And the Chinese, apparently, if I've got this right, the earliest compass was made by them. You pound it out somehow, heat it. I don't know how they did that long ago. Is that really right? I'm not sure, but you hear 4,500 years ago. Make it really thin, maybe float it in water, and have the Earth's magnetic field orient you a little bit. So anyway, they often called these things lodestones, and you'll hear about that. Magnetism's crazy. So they kind of knew about it, and that's where the word magnet comes from, right? The Greeks also, and again, forgive me for leaving out other groups, but just to keep it short, that the Greeks rubbed stuff, and rubbing stuff, or friction, in Greek is called tribo. Okay, so tribo or tribo, probably the right pronunciation. And one of the things that they rubbed, and I should have brought a piece of amber, but you've probably seen amber jewelry, that kind of goldish, clear tree sap, right? Hardened tree sap. So one of the things they rubbed was amber. And so they rubbed different things together, and they noticed this. They were exploring things, and they were good at doing that. And amber in Greek is electro, so that's where the word electro. So we got electro and magnet, or electromagnetism. But they didn't know the connections. They knew that they both could kind of attract and repel, and they saw them as different things. I mean, here's these lodestones, and here's this tree sap that I'm rubbing with stuff. And for a long time, people just, I don't know, it was a novelty, whatever. They didn't really put it to use. It's over 2,000 years ago. Only 200 years ago did people really start to have an organized exploration of this. And then in the century of 1800 to 1900, I call it the electromagnetism century. Certainly other things were done, but phenomenal advances in understanding the connection. Essentially, that's what the 4-month course is, in a lot of ways, understanding the connection between electricity and magnetism and what each is. So Ben Franklin, in about 1800, a little bit earlier, but was a wonderful individual, politically wisdom, neat guy, but he was a scientist, everything. He's sort of a full human, right? A scientist, or a politician, or a musician, or an artist. And he studied this in a very organized way. And what did he do? Well, he rubbed stuff, because they rubbed stuff before, but he rubbed stuff together, and he wanted to see what attracts and what repels. He noticed there was attracting and repelling. Okay, so why did it do it? Why did the things attract and repel? This is important, I know for me, and maybe for you, to realize, don't worry about that. Just explore it. Know what you can know. Some of the stuff's not tangible. If you sit around worrying about why it works, you'll never get anywhere. Maybe that's what people got hung up on. Said, well, just what is going on? Let me organize it and find out. I don't know why. Okay, so, and he died not knowing why. But why does it work? All he knew is that when you rub stuff, it makes them push and pull together, just like amber. So call it electra or electricity or electro whatever. When you rub it, we say the object has been charged. Sometimes people say, if you go to battle, you say charge. So let's do something. Or you might be charged with a crime, I guess. Some people say, that's my duty. I'm charged with this responsibility or this task. Anyway, it's charged. It has the ability to attract or repel electrically or as amber. So he's not worried about it. What he did is organize. So let's see what he did. He basically rubbed stuff, and he took two objects that are rubbed identically the same way, two similar objects. So let me go over here. Back over here and see if I can not employ gravity by having everything fall over. All right. So here's a balloon made out of rubber. Here's human fur. And they used rabbit fur quite a lot. And let me rub this guy. And you'll see you kind of have to get it all around. There's sort of a reason for that. Like, it's magic, right? As far as people knew, what's going on? I don't know, but it's working. Okay, so that's interesting. We'll come back to that in a second. So two of the same things, rubbed the same way, will attract or repel. Right? And we got that repel. And so he went about this process. I'm not going to do it here. You can explore yourself. But sometimes it's a little bit tricky. There's one phenomenon called polarization, which makes it quite tricky. So he found this, that when they're the same, they will repel. Again, it doesn't matter what they are. If you do the same thing to the same type of stuff, they'll push apart. Hang them on strings here. And these guys, of course, will push apart. So they're all the same. And then you go, well, you can imagine, let me just compare A and B. So now, what if A and B, pick my color, attract? And what if B and C repel? Then, what would A and C do? So pause, figure it out, make sure you're clear. So this is the sort of thing he did. He didn't know what happened when I rubbed the thing. He just organized his material and the rubbing process and found this out. So what will it do? Let's see, are A and B the same or different? Well, if they're the same, they push apart. So these two have to be different. Are B and C the same or different? They're the same, not necessarily material or process, but they're charged the same. They have the same electric inclination, whatever that means. So you have things that are the same pushing apart, but that means that these have to be different. But if C is electrically charged, similar to B, then it will do what B does, and of course, they should attract. Good? And that's all he knew. That's all he knew. So why he did not know. Okay? But he made progress because he didn't let that stop him and worry about the ultimate answer. So what he did is he made a list. In fact, you can look up the tribo or triboelectric or electra list. And you'll see different materials rubbed different ways, and they'll be listed and see how charged they are. So when we talk about the strength or amount of electric charge, we look at the strength of the force, how much they push or pull. Charge it more, whatever you're doing, you don't know. If you charge it more, then you're going to get more force of attraction or repulsion. That's all. You don't know what's going on yet. We're about to get to figure that out. We're going to cheat. So, for example, you could rub fur, and you could use rubber or plastic and rub those two things together. Now, I have a little memory aid here. This is important to know. So, if you rub fur with rubber, what you find out is that they're oppositely charged. That's interesting. You rub two things together, they have an opposite effect electrically. If I take glass and silk, so glass and silk or acrylic, I can also get an effect. It's a little hard to show because it can be subtle. So if I took glass and silk, how do I do that? Silk and glass or glass and silk? I'll show you. But I'm going to do glass and silk. Notice I've written them in this order and just worked out that way. And you can continue your list of all things charged in a similar way. So if I rub them, these should do what? Everything in this column should attract or repel. Everything with something else in this column, again, will repel. But any of these two will attract. How strongly is what we call the amount of charge, how much we've given them that ability. That's all. Don't think yet. Okay? So that's 1800 knowledge, right? You're getting there. You're only a couple hundred years behind. So in this class, you're going to take the 100-year journey. We're going to cheat because it helps us visualize this stuff. It's harder to discover stuff than to learn it, as hard as it is to learn it. But atoms, the idea of indivisible bits, was a great idea way back, democratism and so on. It turns out that in this exploration, in this century, people did chemistry, and they did a lot of experiments. And it was in about 1897 that the electron was discovered, thanks to all the great engineers and wonderful equipment that they had, by J.J. Thomson. Look that up. It wasn't until 1911, so 14 years later, that the center of the atom was discovered by Rutherford. He sent these beam of, I'll say, particles, bits, through a gold foil, and he found that as they went through the foil, they would sometimes go straight through and sometimes deflect, as if there was some hard something. And he happened to know, well, we'll talk about that, sort this stuff out. So there's a whole bit, we won't go too far. And then sometime in here, from 1911 to 1932, protons were kind of discovered. And that was like a whole bunch of processes. There had to be something positive there, protons. And then the neutron, which is electrically neutral, it doesn't play. It doesn't play. I probably shouldn't have made this green because it's not electrically neutral. What are you going to do? It's good to think about it. The neutron was discovered in 1932 by a guy named Chadwick. Look all that stuff up. So all this came out of the exploration of electricity and magnetism, and the equipment that came from that. And what happens is it tells us what's going on. Now I just want to mention that then people started colliding, smashing this stuff together, and you find bits or subatomic particles, not just electrons, neutrons and protons, which are the main subatomic particles around us. But you find other things. For example, quarks. 3 quarks make up a proton and 3 quarks make up a neutron. Quark is a weird name, but they gave it kind of a silly name from literature. There are 6 types of quarks. There's up quarks and down quarks. These are made of 2 ups and a down, and these are made of 2 downs and an up, and whatever. So all this crazy stuff, particle physics, that's for later. But what you find when you discover these is that these are electrically charged, and so you have that they go into these categories. Now, when Ben was doing this, he's going, well, they're opposite. You know, there's this way and this way, opposite. So one way mathematically to talk about opposite is plus and minus. So he could have called this plus and this minus, or this plus and this minus. Right? So again, I'm going to call this plus, but he could have called it minus and this minus. Let's just name it. Who cares, left or right, you know, whatever. That way's left, oh, now that way's right. Still that way. So this is what it is. Upon discovering this and realizing that atoms have a center with protons and neutrons holding together by another force called the strong force, which is weird because the protons should push each other apart because they're the same, right? They should push each other apart. Neutrons don't play the electric game, but they play the strong force game, and they help glue it together. Protons attract electrons, they're opposite, and the electrons go around. We'll talk more about that later. But as we go up here and we do the discovery, we find out. Now we get to tell Ben, oh, too bad he died. Oh, well. So we'll still tell him. We'll speak to him in this case. That what's going on here is that the electron inside of the, you can't, if you rip off protons from a carbon atom, you're doing a nuclear reaction. That's bad. Don't do it. When you rub, electrons are transferred. So these lose electrons, and they lose mass, because electrons have mass too. This gains mass, and it gains electrons. Also this way. So that's how I write it. So when you rub things, someone gets electrons and gets a little mass, not very much, and someone loses electrons. The thing that loses electrons has more protons and becomes positively charged, we said. The thing that gains electrons has more electrons, and we say the net charge is negative. So that's what's going on when you're rubbing this triboelectric list of things. It's not obvious, and so it takes really, really careful experiments to figure this out. Now, these materials we call insulators, or not good conductors, so the electrons can just sit there and bunch up. But some materials, electrons, like metals, each metal atom has like 1 to 4 outer electrons that aren't that bound to the atom. They're free to move, called free electrons. And so when you get in a wire, you're going to have electrons moving, not protons. They're stuck in there with a strong force. It's a nuclear reaction you talk about. It's the electrons that tend to move. With hydrogen, which is 1 proton, whatever is red or positive, and 1 electron, it's pretty easy to rip that off. And you can get a beam of protons, that's possible, but often we're talking about the transfer of electrons. So keep that in mind. Now you might ask, well, that's why fur gets charged because it lost electron. That's why rubber got charged because it gained electrons, and so with glass and silk. But why do electrons and protons have electric charge? Why do they play the Amber game? Don't ask that question. Be Ben Franklin. Right now, be Ben Franklin. Because we're not going to get to that in this class. It's past 1900. And so for now, our goal is to try to go, okay, that's what happens, and we're going to cheat, unlike the folks in the 1800s. And we're going to know about atoms, so that's going to help us to think about electrons going, moving around and stuff. So then I would go, hey, that means that electrons go in this category, and protons go in this category, and neutrons don't play electrically. Why? Again, do not worry about that. I'm not going to get anywhere with it right now. It's going to take more investment. Where was I going? Why do materials have electric charge or get charged? Because they can have more or less electrons. Generally, they're neutral. Dust and water in the air will neutralize things, so that balloon probably doesn't react quite as much, does it, anymore? It's been neutralized by the atoms in the air, the dust and the water. Right? So think about the electron transferring, and again, you'll build on that in a deeper way. But hopefully, this makes some sense. Now, I do want to make one last point about this. So you get the idea. It was all known somewhat. They didn't know why. Still not knowing why, Ben does this rubbing, and he says, well, they have the ability to push or pull electrically. Let's call that ability charge, electric charge. Not knowing why. Did some experiments, made a list, and then at the end of the story, finding out that we're transferring electrons. One loses electrons, becomes positive. One gains electrons, becomes negative. People frequently talk about charges. They talk about masses. Look, here's a set of masses. I don't like that. It's fine if you know what you're talking about, if you learn. I mean, these are objects, you know. Here's an object, it has mass. It's maybe not designed for that. I mean, here's a stapler, it has mass. Oh, here's a mass. Everything's a mass. You're a mass, I'm a mass, we're all a mass. Everything, we've got a property of mass, which is inertia and creates and feels gravity, right? So that's a property. It's not the amount of stuff. It's true, if you have more stuff, you have more of that property and that other property. That's weird. Gravity is weird. It's got inertia and the pull of gravity, two different things. So I can still, the balloon has mass, and now it's electrically charged. It's rubber, so it got more mass. It got a few more electrons, not very noticeable. Now, this is kind of fun. 1800, the mass of a proton is about 1,800 times the mass of an electron, and the mass of a neutron is about 1,800 times the mass of an electron. Mass of a proton and neutron are very close to the same, but they're not the same. But just as a little memory aid, kind of cool, that electrons don't add or take much mass. Sometimes you worry about it, sometimes you don't. So when people say masses, they're talking about objects that are used for that property. People say charges. It's really unclear what you're talking about. You could be talking about protons, but usually not in processes like this. Electrons, which are the transferring things. Atoms that are electrically charged positive or negative, so you can have ion flow. So charges is, rather talk, when you're talking electrons, you're talking protons. If it's flowing through a material, almost always it's going to be electrons. So the term charges is loose. We've all heard it a lot, and those of us that know the stuff, maybe we just use it in a sloppy way, but don't be confused by charges. There aren't charges. It doesn't make any sense. There's no charges. Like, I have keys here. Now I don't have keys. Actually, I've got more keys. I have 2 keys. So now I don't have keys, right? And now I have keys, but an electron can't go, here, take my charge. Oh, here, Sam, take my charge. Rudy, I have more charge. Here, take my charge. Now I don't have charge. Electron can't do that. There's something intrinsic about its nature, and that is actually very interesting, but you got to do all the homework and work through the puzzles to get this stuff on a deep level. You will. So try to make it concrete. Imagine electrons going back and forth. Just accept that intrinsically electrons and protons do have this property to attract and repel electrically. Materials can have that usually by one gaining electrons at the expense of the other losing electrons. So that's all we mean by electric charge. We'll talk about the quantity of charge and the letter, either lowercase q or capital Q, in the next video.